This is part 12 in a series of videos in which I'm attempting to repair this Wren executive computer system. As a result of the previous videos in this series, I've been asked to give a bit more detail in some of the fault finding that I'm carrying out. So in this and the next video I thought I'd show some of the detail of how I go about fault finding. Now it does vary from machine to machine and board type to board type and even processor type to processor type. With a Z80 for example, it's a very different approach that I use for testing the in-out system that I would for other types of processor, just because of the way the different processors actually work in terms of in-out addressing and the way that the instructions are executed. Also, the equipment I use will vary depending on the physical layout of the board, the processor type, the type of architecture, and what the fault is I'm trying to track down. So I'm showing a whole range of different methods that I use in this particular repair. Hopefully some of this information will be useful, but the overall point is to try and show that there are many different ways to approach fault finding, and there isn't any particular right way of doing it. It's whatever works and whatever equipment that you have. So in this video we'll be looking at some very basic fault finding using the logic analyzer, and in the next video we'll look at some more detailed types of testing that we can carry out using the Fluke 9010A. If you've been watching the previous videos, you'll know that although I've now got this machine to boot to the welcome screen, it won't try and read or write the floppy drive. And there are also some other issues I haven't mentioned yet, but we'll come to those as we progress. So the approach I've been taking is to go around and look for obvious candidates or culprits for these faults. And I know that there is a fault somewhere in some of the control lines that are being used to access the serial chip and also the keyboard controller. And in this video I'll show you how I've gone about determining that. I mean, firstly they don't work, so obviously there's something wrong. But obviously the next step is to try and figure out why they don't work and to try and narrow that down. Now more recently I've been using the logic comparator to do this. This is a unit I've designed recently and I've started using it, and it is extremely useful. It does save a lot of time. I've shown this briefly in previous videos, but I won't be using it in this video because most people won't have one of these, at least not yet. If you want one, or at least a set of bare boards, then let me know. What I'll be using instead is the approach that I have used up until the point when I had the logic comparator. There are two general approaches you can take. You can use a scope or the logic analyzer. So the basic approach that I take when I have a number of similar devices that I want to test is to attach a test clip to the logic analyzer. And the logic analyzer is configured to allow me to test certain chip types. So in this case this clip is attached to an LS244, and the analyzer is set up to allow me to test that particular chip type. I can then move the test clip from device to device and test all the same type devices on the board, or at least the ones that I suspect may have an issue. So we'll take a quick look at the spec sheet for the LS244, and as we can see it's an octal 3-state buffer. The 8 buffers are arranged in 2 sets of 4, and each of those 2 sets has its own control line, and when the control lines are high the outputs of the buffers are in tri-state mode, so they're just in high impedance mode and they float. One of the reasons it can be difficult to test a device like this in circuit is because the outputs are quite often connected to common buses. So you might have a number of these or similar devices where the outputs are all connected to a common bus, and so that bus might be active all the time and you'll see switching on the outputs even though that switching may not be coming from this particular device. And so it can be difficult by just putting a scope on there to determine whether the output that you're seeing changing is because this device is switching or because there's something else on the same bus that's switching. So it's often easier to use a logic analyzer to do testing of these devices or of course the logic comparator I can now use as well. So we'll look at the logic analyzer, and the thing to bear in mind with these devices is sometimes they are used to take advantage of the tri-state outputs, and other times the control lines are just hardwired to ground, in which case these are used just as permanent buffers that are on all the time. These can also be used to tidy up signals for increasing fan out. They've got Schmidt trigger inputs, so they do tend to be relatively immune to noise, or they might just be used for timing purposes to introduce a short delay. Either way, when the input to the control line is low, the output should mirror the input. It should be exactly the same. They're not inverting, so it should be, if the input goes high, the output should go high as well. So we'll look at the logic analyzer and I'll show you how I've got it configured. Okay, I'll power up the logic analyzer, and what I have configured with the analyzer is a separate directory, and in that directory I have a configuration for each of the main 7.4 series type ICs that I need to test. If a new one comes along, then I'll just add a new configuration, but it does mean it's very quick and easy to set up the analyzer to test particular device types. So in this case we are looking for the LS244, so I'll just switch to the correct directory. And now I want the LS244. And the analyzer is now configured for the LS244. The way I tend to configure these is to use a common connection regime as much as I can, but it only takes a few minutes to connect a suitable test clip, and then I'm ready to start testing the devices. If we look at the formats for this, then it's quite straightforward in the way it's configured. For the 244 we have two sets of 4 buffers, so I've configured it so that I've got a set of 4 inputs, set of 4 outputs, and I'll call those A in and A out, and then we have the same for the second set of inputs and outputs, and I'll call those B in and B out, and then we have 2 enable lines, A enable and B enable, and it's as simple as that. That's all we need. We can now go to the trigger and decide how we want to trigger the analyzer, and in this case, as you can see, we've got it to set on the B enable line. So I'll change that and we'll look at the A enable line to start with. So I'll set that to don't care. We know these are active low, so I'll set 0, and then we can go to the waveform. I'll now power up the Wren. And the Wren has completed its self-test, which you saw in previous videos. I've got the welcome screen showing, and what I can do now is arm the analyzer. So I'll arm it, and you can see that immediately it triggers. Now I have tested this device, and the 2 enable lines are permanently attached to ground. So this particular device is always active. It's never tri-stated, and that means when we trigger it we should always see the same inputs and outputs. So even though I have input enable line A selected as the trigger, because the 2 enable lines are both always connected to the ground, we should always see the same for the input and output on both sets of 4 buffers. When they're separate, what you need to do is to switch the trigger between the 2. So if you want to look at the A set of buffers, trigger on the A enable, and if you want to look at the second set, then trigger on the B enable. We don't actually need to do that on this particular buffer, simply because, as I say, the 2 enable lines are permanently attached to ground. But that does mean that we can see a problem straight away here, and that I'll keep arming it and we'll keep repeating the capture. You can see that although the input is changing, and the inputs here are the top traces, you can see we've got A in, A out, B in, B out, and you can also see that the two enable lines are always low. And we can see here that A is fine, the input is the same as the output, or at least it is with the value of E going into the input. But we can see that we have an issue with the fourth bit on the B output, and that it should be a 0 but it's set to 1, so we should have a value of 2 on the output and we've got a value of A. So A is 1010, so that first 1 is obviously incorrect. So what we can do is scroll across and see if we can see any other values that are incorrect. You might get transient values like this. If it's a single clock width, you can ignore it, that's most likely a transient switching. Bear in mind we are triggering or collecting data on the analyzer using state mode on both clock edges. So sometimes you'll get transient values, but if they are just one clock width wide, then you can ignore them. So we'll keep scrolling across until we see something a bit more significant. And here again we have a value of 0 going into the buffer and a value of 8 coming out, which again is bit 4 is stuck high. And you can keep going across. Now in the next video what we'll look at is using the fluke to explicitly manipulate these values so we can test all the possible permutations, because for buffer set A we're only testing a value of E, and it could be that there's a stuck bit there as well. This is where the logic comparator is much more useful, because it will allow you to run, and essentially it will continually scan as the machine's running, and the lights will flash if there's ever any mismatch. So we obviously have an issue with this particular buffer chip. What we'll do is have a quick look at the scope trace and see if we see anything on the scope to back up what we're seeing on the analyzer. So I'll turn the analyzer off and move the camera so we can see the scope screen. Okay, so we're looking at the scope. I've got channel 1, which is the yellow channel, hooked to the input of the buffer, and channel 2 hooked to the output, and you can see straight away that they're doing different things. So if we do a single shot capture, you can see that while the output is changing, the input is always low. So there's obviously something wrong with that buffer chip. So what you could do at this point is check the other channels to make sure that there are possibly faults on those as well. But if there's a fault on one channel, then of course we need to change the chip anyway. I have actually checked to see where these two connections go to, and one goes to the output goes to the serial controller chip, and the input is from some glue logic, and that goes to back up the particular fault I was looking for here. So what I'll do now is I'll replace that device, and then we'll get to the analyzer back on and we'll see if we've resolved the problem. Okay, so I've removed the chip. I tend to remove chips intact. I very rarely cut the pins off. I know some people prefer to cut the pins off and remove the pins one at a time, but I tend to remove devices and I try not to damage them or overheat them. I want to know if they were actually faulty, and that just gives me more information for the future, and I can kind of keep learning as I repair more and more devices. So I've taken the device out. We'll test that in a few minutes. I've cleaned up the board. I've used IPA on both sides to give it a really good clean, and as you can see, the board is now ready to accept the new device. I'm going to use a socket, of course, and then we'll put it back on test and see if that's resolved the fault. So I've fitted a socket. I've installed a new 244 buffer chip. We've got the analyzer back up and running, and that's connected back to the same device, so it's now connected exactly as it was before. And we'll do a capture and see what we get. And as we can see, whereas before we were getting 2 at the top and E at the bottom, so 2 going into the buffers and A coming out. We can see now that we're getting the correct value. So I'll run it a few times and you can see that we are now getting the right value each time on both sets of 4 buffers. Now, one of the reasons I like to take chips out intact, as I say, this is the device I took out. I'm now going to install it into the IC tester and we'll see if we get a faulty device. Now, one of the reasons I developed the logic comparator was because sometimes you see devices that will pass on a IC tester, but the logic comparator will flag them as faulty. So this is the device in the IC tester. This is the one I took out, and as you can see, it passes the test. So this IC tester is showing this device as not faulty, even though we know it wasn't working in the board. And this, again, it's one of these marginal cases, and it's the reason I do this sort of testing, is to make sure that I've weeded out any weak components. It's also the reason I don't cut the pins off devices when I remove them. I want to be able to see exactly what was going on the board, and it resolves any question marks I may otherwise have as to why the board wasn't working when the signals kind of looked okay. So with marginal cases, it's not necessarily the problem with the device you take out. It might be the devices it's feeding into, and so that's why I need to know if the chip itself is at fault. Now, because this one is indicating as being okay, I now know I need to look at the device that it was feeding from pin 9, and if I just cut the pins off, swap the device, put a new one in, and the fault had gone away, I wouldn't be any the wiser. I'd assume that I'd completely rectified the fault, and that may be the case, but I won't know that until I fully investigate the device that pin 9 was trying to switch. So that's the approach I take. It may seem to be slow and long-winded, but it does save a lot of time in the long run. I don't end up chasing myself in small circles trying to figure out why I've replaced a part that seemed to be faulty, and yet now it's still seeming to be faulty and the machine's still not working. It doesn't actually take as long as it may appear to set this up. Once you've got the configuration set on your analyzer, you can store those to hard disk, and it then just takes 1 or 2 minutes to test each type of device. And what I can do now, of course, is move the test clip to the next 244 and test that one as well. In fact, I've been around the entire board and that was the only 244 that was showing any problems. What I'm going to do now is to move on to the 245s. They're actually far more likely to cause issues because they're bidirectional, and so if there's a problem in controlling them, you can end up with contention on the inputs or outputs of them, and that can damage them. So I'll go around the board and test those, and then we'll see if we get any further through the process in trying to make the floppy drive work. I suspect it won't. I think it's a floppy drive controller failure, but I still need to sort out the issues with the remaining devices and the other small faults that still remain. Any questions, then please leave a comment, or if you want to see more of this sort of testing, then let me know.